Hello, I am BK Teja Mekla, working under Dr. Leslie Frame in the University of Connecticut. I would like to talk about my work as it's shown in the title Prediction and Prevention of Bridge Performance Degradation Due to Corrosion, Material Loss, and Microstructural Changes. This work mainly focuses about the steel corrosion, the steel that is used for the bridge construction. As it is mentioned in the title, this work focuses on the low alloy steels A7, A36, and A588 to study the general corrosion properties and to produce a model at the end of the study to predict corrosion performance of the bridge. Before going into the details, I would like to share a couple of facts that the bridges in the USA share the 37% of the annual total cost of the corrosion. And on top of that, more than 50% of the bridges in Connecticut were estimated to be either fair or poor in condition by the Department of Transportation. And I would like to give a little bit background about the low alloy steels that are used for the bridge construction. A7 steel is one steel that is used for the bridge construction till 1960s, and as it is shown in the table, the composition of the A7 does not specify any limits regarding the alloying elements except copper, phosphorus, and sulfur. One big limitation of A7 steel is that it is poor in corrosive properties and it's not robust mechanically. And with many modifications, A36 steel was developed where it specifies the limit of carbon, silicon, along with copper, phosphorus, and sulfur. But still, A7 steel was not uh, very good in its corrosive properties. Later, in the very recent years, A588 is also called weathering steel was developed. And another reason uh, why the bridges in Connecticut face a poor corrosive properties is because of the marine environments will pose salt in its environment. And even the de-icing salt that is applied during the winters also causes problems to cause the corrosion by providing the chloride ion. Now I would like to talk about how we would like to deal and perform the study to understand the corrosive properties of these steels. We used wet dry cycle testing method as is shown in the figure. We took water tanks of 10 gallons in size each, and each tank is designated for a specific salt concentration, and four salt concentrations were used: 1, 2, 3.5, and 5.8%. And two surface conditions of the samples were used: oxidized and polished. And in the wet dry cycle testing, each wetting time in the cycle is 15 minutes and drying is for 1 hour, and 400 such cycles were performed. And batches of samples were collected at different time points as it was shown in the table, and each sample dimensions were 50 mm, 25 mm, 4.76 mm, and the samples collected were photographed using Nikon 5000 DSLR camera for surface composition. And once the samples were collected, X-ray diffraction was performed to confirm the phases present in the corrosion products, and the parameters used for mentioned here in the 2 theta range of 10 degrees to 65 degrees and speed of 5 degrees per minute with a step size of 0.02 degrees per step. And Bragg-Brentano method was used for the powders and with the XRF reduction mode. Scanning electron microscopy is also used for surface morphology study and to compare the sizes of various features of the products. Now, I would like to talk about the results. Uh, before I dig into the results, I would like to start with different products of the corrosion that will be observed in the photography and SEM. The four products are magnetite, alpha, beta, gamma, FeOH. Most of the products are in the morphology of cotton ball shape, differing in the features that are present on the cotton ball. Magnetite has dense plate features, and alpha FeOH has fine viscous on the cotton ball. Beta FeOH has thick dendrite shapes on the cotton ball, whereas gamma FeOH has flake or fine plate. But this gamma FeOH is found only during the initial stages of the uh, the corrosion formation, and it is not expected to be present in 400 cycles. So uh, I would like to start with the photographs of the samples. uh, A7, A36, A588 samples was shown here, and every sample has two colors, black and the orange. The black color region is for magnetite and orange is for alpha or beta FeOH. And we can see that black is present usually at the edges or corners, and orange is at the center or interior regions. So we can say that the magnetite is usually at the corners and the edges, and interior has alpha and beta FeOH. Coming to the SCM images, uh, we can see the presence of various phases. For example, this is big cotton ball structure, as we were talking before, with the very good dendritic structures. And as we can see here, we can see very good dendritic structures. And this figures corresponding to the alpha FeOH with small cotton ball with flaky structures. Uh, Sorry, it is with the fine viscous structures. And this will correspond to small cotton ball with densely packed. So this can be called as magnetite, and this is again alpha FeOH. This is magnetite, and this is beta FeOH. This is alpha FeOH, and this is magnetite. So uh, SCM is used for confirming the presence of different products. Coming to the XRD, we can see the presence of beta peak, and this peak also increases in its size with increase in the salt concentration. And even in case of alpha, the alpha is growing with increase in the salt concentration. Beta formation is really dangerous for the bridge performance because of the figures, because of the region explained through these figures. So when the beta is formed at the interface, the corrosion products will spill off in the form of layers like this. So because of this forming, the product that is formed is no more a protective product, and hinder the uh, that will hinder the corrosion performance of the steel without forming a protective layer. So the presence of beta is not at all desirable, since it hampers the very good surface properties. And we can see the similar performance of even A36 and A588, that beta will increase with the salt concentration as alpha. And but the beta peak is really high in the case of A7, and less in A36, and very less in A588. So coming to the conclusions, we can say that alpha and beta phases increase with NaCl percentage, and less magnetite formation is compared to the field collected samples. The field collected samples overall occupy the blackish regions. That's why we can say that they are all full of magnetite. But here in the 400 cycle samples, magnetite formation is very less. And the we have seen the morphology of alpha, beta, and magnetite, and we also have seen the effect of geometry, that adjacent corners have more magnetite and interior regions contain uh, high alpha FeOH. And even the formation of beta is higher in A7 and lesser in A36 and A588. So about ongoing work, we wanted to study the electrochemical studies and characterization of cross section. And finally, I would like to thank Transportation Infrastructure Durability Center at the University of Maine. I would like to thank the Frame Lab Group, and I would like to thank the staff in the Yukon helped me. Thank you.